Testing, 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 testing. Volume seems good. The microphone's a little bit further away, so I have to make sure. Alrighty. Welcome to another Hupo stream. Hope you guys had a good weekend. We're going to start off with a paper this week. This is a paper that was recommended by someone on the Discord, so props to that community there. We even had a little discussion going on this morning about segment anything's embedding space. So this paper is a little bit older at this point. This is 9 October 2022. So when I first saw this paper, my first impression is this seems like kind of an ancient paper. I don't know about reading an old paper like this, but then I saw University of Texas at Austin, which is right next to where I live. So I was like, okay, that's kind of interesting. I'm curious about what they're doing over there at U Texas. And then I also saw this comes out of Microsoft AI. So to me, both of these institutions are interesting. Obviously, Microsoft, they have all the HoloLens stuff, but they also have all the OpenAI stuff now. And then University of Texas Austin, kind of nearby where I live. And Gans with diffusion, kind of a cool concept. So, hey, I think that brought me over the edge, and that's why I decided to read this paper. So we'll see what they have to say. Lots of different math here. They even have a theorem in here. So, yeah, theoretical analysis. So I don't know. We'll see what kind of math-heavy take they have for this. So let me readjust this, and let's get started here. All right, we got generative adversarial networks, aka GANs, are challenging to train stably. Yeah, challenging to train. The reason they're challenging to train is because you have this discriminator and generator, and they're kind of constantly fighting over one another. And if the discriminator gets much better than the generator, or the generator gets much better than the discriminator, then you can basically have this mode collapse that happens where the kind of little embedding space, little latent that they compress into just becomes no good. So there's other types of GANs that try to solve this. I think a term that pops up in my head is Wasserstein-GAN. Wasserstein-GAN. Yeah, this one. But GANs were popular for probably 5 years, so there's hundreds of GANs papers. So there's definitely no shortage of ideas on how to make GANs better, and yeah, maybe some of these papers come back. Promising remedy of injecting instance noise into the discriminator input has not been very effective in practice. So the discriminator is the part of the GAN that tries to determine whether an image is real or fake, whether it has been generated or whether it forms part of the original data distribution. So injecting noise into that is you're basically saying, okay, the generator is going to produce an image, or I'm going to take an image from my image distribution, I'm going to put noise on top of it, and hopefully that acts as a form of kind of augmentation for the discriminator, but not very effective. In this paper, we propose Diffusion-GAN, a novel GAN framework that leverages a forward diffusion chain. Kind of interesting they call it chain here, right? I feel like at this point people would call it a forward diffusion process, or, right, they're just referring to the fact that diffusion models, you are adding noise iteratively over a bunch of time steps. Look how many time steps they have here. 1,000 timestamps. I don't think we've seen a single diffusion paper in modern times that has that many time steps. So this is quite a lot of time steps for diffusion here. To generate Gaussian mixture distributed instant noise. Gaussian mixture just basically means a bunch of Gaussians together. So you can have one Gaussian, and then you can have two Gaussians, and you're going to have two little bumps in your distribution. You can have three Gaussians. You can have n Gaussians, right? A mixture of Gaussian just means you're kind of using a bunch of different Gaussians to make one distribution. Diffusion-GAN consists of three components, including 1, adaptive diffusion process, 2, a diffusion time step dependent discriminator, and 3, the generator. Okay, so basically the diffusion is really only part of the discriminator, and it seems like the generator is largely unchanged. Both the observed and generated data are diffused by the same adaptive diffusion process. So observed, I guess, probably refers to the original image distribution. At each diffusion time step, there is a different noise to data ratio, and the time step dependent discriminator learns to distinguish the diffused real data from the diffused generated data. Okay. So the discriminator is going to basically be able to distinguish between the real and the generated data, but only within the diffusion process. So it's going to be discriminating increasingly noisy versions of the images, which is kind of what you see here in this picture. The generator learns from the discriminator's feedback by backpropagating through the forward diffusion train, whose length is adaptively adjusted to balance the ratio and data levels. So, all right, well, actually, we'll just wait to see exactly what they mean there by backpropagating through the forward diffusion chain, because there's different parts of the diffusion model, right? There's like the actual noise that is getting added. There's the thing that's trying to predict the actual noise. And I don't exactly know what they mean there. Length is adaptively adjusted to balance the noise and data levels. So length here, I think they're referring to the length of the diffusion step or diffusion chain, so how many steps you have. We theoretically show that the discriminator's time step dependent strategy gives consistent and helpful guidance to the generator, enabling it to match the true data distribution. So the true data distribution is going to be your actual image data set. So it seems like here they're using one of these face data sets. These face data sets were very popular in the GAN era because it's basically you just have these data sets. I think Celeb A is a common one, but it's basically these thumbnail pictures of celebrity faces like this, and these were very popular for GANs because they're actually quite small and they're very consistent. You know, it's always the same kind of framing of the face and so on. But they've kind of fallen out of fashion just because there's such a limited distribution. We demonstrate the advantages of Diffusion-GAN over strong GAN baselines on various datasets, showing that it can produce more realistic images with higher stability and data efficiency. All right, so there you go. There's the claim, is that you get more realistic, higher stability, and data efficiency. Generative adversarial networks, GANs. This is the original GAN paper. This is the original author, Ian Goodfellow, who I think now works at Apple. I'm not entirely sure. And their variants, Brock et al., Karas, Zhao. So you can see here, this is kind of the GAN era, 2019 all the way to 2020. Have achieved great success in synthesizing photorealistic high-resolution images. GAN in practice, however, are known to suffer from a variety of issues ranging from non-convergence and training instability to mode collapse. So this is kind of what I was referring to, where the lower dimensional space that the discriminator and the generator share collapses, which means that rather than being nice and evenly spread all over the lower dimensional space, it kind of like becomes one tiny area and all things kind of start looking the same. Analysis and modifications. This is a very busy reference section. I kind of don't like how they put the entire name of the paper, because it makes it very, look at this, most of the sentence is basically just a reference. I kind of prefer the references that's just a number rather than the entire full name of the people. Changing the objective functions, regularizing the weights, utilizing side information, adding a mapping from the data to the latent representation, and applying differentiable data augmentation. Okay, so these are all a bunch of different GAN papers. A simple technique to stabilize GAN training is to inject instance noise, i.e. to add noise to the discriminator input. So this is the kind of augmentation that they're talking about, where you can take the input to the discriminator, and the output of the discriminator is basically, is this real or not? It's just performing kind of classification. So you're injecting noise into that. So basically a form of data augmentation or regularization. Both can widen the support of both the generator and discriminator and prevent the discriminator from overfitting. However, this technique is hard to implement in practice as finding a suitable noise distribution is challenging. Okay, interesting. Show that adding instance noise to the high-dimensional discriminator input does not work well, and propose it to approximate it by adding a zero-centered gradient penalty on the discriminator. What is this? Zero-centered gradient penalty. Maybe this is a regularization term that prevents the gradient from being too big, something like that. Almost like a gradient clipping kind of situation, but I don't know. Comes from this paper, Roth et al. 2017. This approach is theoretically and empirically shown to converge in this other paper in 2018 that also demonstrated that adding a zero-centered gradient penalties to non-saturating GANs can result in stable training and better or comparable generation quality compared to Wasserstein GAN GP. I don't know what this is, but I'm assuming this is probably just a version of the GAN that uses this zero-centered gradient penalty. Caution that zero-centered gradient penalties and other similar regularization methods may stabilize training at the cost of generation performance. Okay, so you have people who say, hey, here's a trick to stabilize the training, and then you have papers later that say, hey, you stabilize the training, but the actual image generation quality is worse, so some of these tricks aren't necessarily improving. There has been no existing work that is able to empirically demonstrate the success of using instance noise and GAN training on high-dimensional image data. So I think here they're referring to a GAN. So there's a lot of different types of GANs, and I think the one that I was kind of officially referring to is a VQ GAN, where the generator and the discriminator are compressed into this quantized latent space, right, where you have a code book, kind of like a tokenizer in an LLM, right? There's a specific set of tokens, specific set of codes, right? This quantization between the generator and then the discriminator. But here they're talking about doing it directly in image space, which is what they mean here by high-dimensional input, because the discriminator is looking at the actual image itself. So it makes sense, right? But it doesn't necessarily, I think the reason you can do that is because I bet you these images are very low dimensional. So that's why you can basically do diffusion and discrimination directly in the image space like this. But what's interesting is that I feel like nowadays most people don't do the diffusion in the image space. They do it in a compressed latent space. So you could probably do something like that. You could probably do whatever this paper is doing, but in the compressed latent space as opposed to in the image space. And maybe that works better. Maybe it doesn't work better, but it's potential future work. To inject proper instance noise that can facilitate GAN training, we introduced Diffusion-GAN, which uses a diffusion process to generate Gaussian mixture distributed instance noise. Okay, so that's the actual noise that is being generated with the diffusion. I don't know if that's not, is that really, if you look at a normal diffusion model, is that the same type of noise? Is that the type of noise that most stable diffusion models add? Gaussian noise? Is there other types of noise? Maybe it's always Gaussian noise? I feel like I vaguely recall people having different types of noise that they add, but I don't remember enough to actually say. All right. Show a graphical representation of Diffusion-GAN in Figure 1. In Diffusion-GAN, the input to the diffusion process is either a real or a generated image, and the diffusion process consists of a series of steps that gradually add noise to the image. The number of diffusion steps is not fixed. okay, but depends on the data and the generator. We also designed the diffusion process to be differentiable, which means that we can compute the derivative of the output with respect to the input. Okay. So here you go. Diffusion process. We don't know what these equations mean yet. We're going to have to wait to see. Actually, why don't we just read it to the point where we get the equations and then look at the paper, but they're not going to even show us that. So maybe let's just see if we can kind of infer what they mean. This probably means image sampled from a distribution of images. So this is your real image. Your generator, xg, is whatever. I'm not going to try to infer the value for those variables. Let's just wait to see this figure until we know what those variables mean. Unlike vanilla GANs, which compare the real and generated images directly, Diffusion-GAN compares the noisy versions of them, which are obtained by sampling from the Gaussian mixture distribution over the diffusion steps with the help of our time step dependent discriminator. Okay, so the discriminator is not just, it's going to be conditioned on the time step. I bet you that's probably what's going to happen. Yeah, and look at here. So this is probably the discriminator function, and you see how it's conditioned on the time step t. So I bet you that's probably what's going to happen. This discriminator has the property that its components have a different noise to data ratios, right? As you go further and further in the time step of the diffusion, you're going to have more and more noise, which means that some components can add more noise than others. By sampling from this distribution, we can achieve two benefits. We can stabilize the training by first easing the problem of vanishing gradients, which occur when the data and the generator distributions are too different. Okay, so if the actual data distribution, which is your actual images, and then your distribution that comes out of your generator are too different, then I guess you get vanishing gradients from that. Generally, vanishing gradients to me refers to when you're trying to push gradients into a very deep neural network, and by the time you get to the lower layers, it's kind of has vanished. And I feel like skip connections largely solve that, so I don't know exactly what they mean here by that. Second, we can augment the data by creating different noisy versions of the same image. Yeah, so it's kind of a form of dataset augmentation. Improves the data efficiency and the diversity of the generator. Data efficiency here means you get more signal out of the same amount of data, right? So any kind of augmentation technique is going to improve your data efficiency. Boo, you have anything to say? She's yelling. We provide a theoretical analysis and show that the min-max objective function of Diffusion-GAN, which measures the difference between the data and the generator distributions, is continuous and differentiable everywhere. So at a high level, we say things like we want the images from the real image data set and the images that are generated to be the same, but you can say that in statistical kind of jargon, and in statistical jargon, what you really want is the distribution of images, right? The distribution of your data to be the same as the distribution that comes out of your generator. So really, you're trying to take two distributions and get them closer together, right? It just so happens that the distributions are representing images, but you can always think of things in statistical terms, and that's what they mean. But really what they're saying here is just the images that are coming out of the generator should match the images of your actual data set. This means that the generator, in theory, can always receive a useful gradient from the discriminator and improve its performance. Useful gradient. Our main contributions include, right, so here are the little section at the end of the introduction where they basically say everything that they did and all the novel contributions of this paper, so that someone who's reviewing this paper can very clearly say, hey, here are the 4 things that this paper adds and whether or not I'm going to accept this paper to the conference. We show both theoretically and empirically how the diffusion process can be utilized to provide a model and domain agnostic differentiable augmentation. Model and domain agnostic to me means that this works over a variety of different model architectures. Data efficient and leaking free. I don't know what leaking free means there, but extensive experiments show that Diffusion-GAN boosts the stability and generation performance of strong baselines, including Style-GAN 2. Style-GAN was a popular GAN framework back in the day because it actually had like a nice repo that you could use. Yeah. This repo was very good. This is quite old at this point, though. Look at that, 5 years ago. Isn't this the guy? I think this might be the dude who did the diffusion models. Yeah, this is the guy who did the... Oh, no, follow. This guy did the paper that we read about diffusion models that looked at different kind of mathematical parts of the diffusion model. Oh, shit. Yeah, this paper. We read this paper on the stream where he went deep into diffusion models and looked at all the different like samplers and the types of noise and the number of steps and all the different parts, and kind of did a hyperparameter sweep effectively over all the different parts of the design space for diffusion models. I did not know that he was also in charge of Style-GAN. That's kind of cool. Achieving state-of-the-art results in synthesizing photorealistic images as measured by our favorite Fréchet inception distance, FID, and recall score. So 2 different quantitative metrics here. Preliminaries, GANs and diffusion-based generative models. So here they're going to explain GANs, and then they're going to explain diffusion models. So let's see how they explain GANs. All right. GANs are a class of generative models that aim to learn the data distribution. So you have some distribution over your data, right? In this case, it's images of a target data set by setting up a min-max game between 2 neural networks, a generator and a discriminator. Right? You have 2 different neural nets. First one is called your generator, G. Takes as input a random noise vector, Z, sampled from a simple prior distribution. Right? So some vector in, I don't know, some noise distribution, such as a standard, normal, or uniform distribution. So normal is just a Gaussian distribution, right? The bell curve, and then uniform is just uniform over all space. So every point in that space has an equal probability of being sampled, and tries to produce realistic samples, realistic looking samples, G of Z, right? So your generator is going to take in that noise vector, Z, and it's going to produce some image X that hopefully is as close as possible to the original P of X distribution. The discriminator D receives either the real data sample X, drawn from P of X, or a fake data sample G of Z, generated by Z. Or generated by G, which is the generator. So the generator generates basically these X's, and you can either take the X from the original data distribution or from the generator, and tries to correctly classify them as real or fake. So the discriminator is basically just doing a classification task. The goal of G is to fool D into making mistakes, while the goal of D is to accurately distinguish G of Z from X. So, I mean, this is a little bit of anthropomorphization here, but the min-max objective function of the GAN is given by this. So min-max objective function means that you have basically a maximization process occurring inside a minimization process, and it's the generator that gives you this certain and there's you can kind of keep infinitely wrapping if you want to do that. Oh shit. But let's actually look at it here. So you have, oh my god, I'm just sloppy with the mouse today, my bad. So you have the generator, right, that's given some noise vector z. It produces an image x. That image x goes into the discriminator, right? The discriminator is basically going to give you the probability. It's a binary classification, so it's going to say 100% this is a real image, or 0% this is a real image, right? So it's going to give you some probability there, right? That's why you can just do 1 minus that. Log probability, the expected value of that. So the expected value of that, given that your z is sampled from a probability distribution of z's, right? A distribution of z's, right? Which is your noise. You're adding that here to this, which is the discriminator, and here you're just giving it x, which is, oh my god. See, this is the other problem with big references, is that when I accidentally click anywhere in the paper, it automatically sends me all the way to the bottom. Okay, so here your discriminator is receiving the generated image, and then here the discriminator is receiving the real image, and the real image is sampled from a probability distribution of over x, right, where x is the p of x is your real image data set. Also probability, also log probability. You add those two together here, and you want the discriminator that maximizes this term, right? So, and then you want the generator that minimizes that term. So they're competing against each other. And I guess they called this function v because they call it the vanilla objective function, and they're probably going to add their own special terms to that. Vanilla objective function is often modified to improve the stability and performance of GANs, but the general idea of adversarial learning between G and D remains the same. Diffusion-based generative models, Ho et al., assume this. So what do we got here? We got x1 to xt are latent variables of the same dimensionality as the data. So this is a little bit more confusing here, because now they're using x to represent images, but here they're using x to represent the latent variables in the diffusion process. So here you have an integral over this p of theta, which is a model. Where do they define it? They don't even tell you what p of theta is. But p of theta from x at time step 0 all the way to x at time step capital T, you're integrating this over x from 1 to capital T, and the integral of that is equal to whatever p of theta x naught is. I think p of theta is the diffusion model? I don't know what else it would be, but it's kind of weird that they don't actually define that specifically. Gradually add noise to the data. So this is the noise distribution, Q of x naught. X naught is sampled from that in T steps. Total of T steps of diffusion in your forward diffusion chain or in your diffusion process. Predefine variance schedule beta T. So the amount of variance in your noise distribution is probably going to change as you go further and further into the diffusion process, right? This is something that we've seen again and again, where at the beginning you're only adding a little bit of noise, right? The variance of the noise that you're adding is small, I guess, and then as you go further and further and further, the nature of the noise distribution changes, right? This is also kind of backwards. Let me see this. Diffusion model images. I think in most diffusion models, capital time step T is, yeah, look at that. This paper is so old that it's backwards. So in most diffusion models, at time step 0, you have the pure image, and then at time step capital T, you have the full noise. Okay, never mind, I'm wrong. This is also the case here. At time step T, you have the full noise, and at time step 0, you have the pure image. Okay, so never mind. That is what they do. But you see here how they also have the variance schedule to the Gaussian noise with beta t. So there you go. The variance schedule beta t. And the actual variance sigma squared here. So here you have beta t times the variance times the identity matrix here, right? Because this is a normal distribution over higher dimensions, right? So when you're defining a normal distribution over more than in a normal distribution or a Gaussian in one dimension, it just has one number, which is the mean, and then one number, which is the variance. But if you define a Gaussian over multiple dimensions, right, you're going to have you're going to have however many means for however many dimensions, and you're going to have basically the same however many variances for however many dimensions as well. And this doesn't necessarily need to be the identity matrix here. You could have more complicated noise for a multidimensional normal distribution, but generally people don't want to mess with that. So generally you're going to see this identity matrix here, which is just a diagonal, right? It's just a bunch of zeros with ones in the diagonal. So here you have 1 minus beta t times the actual xt minus 1. So the noise is going to, or the variance is going to increase or decrease as we get into a higher t, one of those two. And then here you have the actual x of t, which is the image at time step t. Q of x of t given x of t minus 1. So here you're trying to predict the image at time step t given the image at time step t minus 1. And in order to do that, right, since all you're doing is just going from, let me actually do this. Let me copy image. Can I just like paste this image in a new tab just so I don't need to keep scrolling up and down? Duplicate. Yeah, I'm gonna do this, and I'm gonna put the image here just so we can always reference it without having to constantly scroll up and down, because or else you guys are gonna get a little tired of scrolling up and down. But yeah, if you go from a time step, for example, 100 to time step 101, you're going to be adding noise, which is what they're showing you here in this equation, right? Is they're going from time step t given time step t minus 1. So this could be time step 100 given time step 99, as basically all you're doing is just adding this Gaussian noise to the image. All right, and then what is this first equation here? This first equation here is saying q of x from 1 to capital T given x of x naught. So x naught is the very first one, right? So basically the original image. Here you have this giant pi is basically multiplication, so it's like a summation symbol, but instead of summing every single term, you're multiplying every single term. So you're multiplying every single one of these from time step t equals 1 to time step capital T, right? And this q is actually this q right here. I don't know where do they define q exactly? For diffusion chain that gradually adds noise to the data. This is a little confusing. Like, generally, if you're going to have these type of equations, like, they should tell you exactly what p of theta is and what q is. They're kind of just like not telling you exactly what it is, and they're kind of forcing you to intuit what it is. A notable property is that xt at an arbitrary time step t can be sampled in the closed form. Okay, so I guess here what they're saying is that because you're adding the same noise every time, or not the same noise because there's obviously that schedule on the noise, but because you know if you give someone the time step, they can tell you exactly the noise that you would add to that, and they can tell you not just the noise that you would add at that time step, but also the noise that you would add at every previous time step. It means that if you want the image at time step 600, you don't necessarily need to calculate every single, or you don't need to add noise 600 times. What you can just do is say, okay, here's the original one. I'm going to basically plug it into this equation, which is basically going to multiply this Gaussian noise however many 600 times, and then I should be able to get the 600th image instantly. Well, not instantly. You still have to do all this multiplication here, but you can basically get the image at any arbitrary time step. Okay, they're introducing a new variable here, alpha t, which is basically just 1 minus beta t, where alpha t is s equals 1 to t of alpha s. I don't know why they feel the need to do that. Right? This just seems like a extra confusing here. Why just rewrite this equation in terms of beta? You don't have to introduce this new variable alpha here. Right? Like you look at here, square root of 1 minus beta. This is the same as square root of alpha t. But maybe there's a reason for that. Maybe they're introducing this alpha because they're going to do something tricky. Sometimes in the equations, like they'll bundle and they'll separate it out and they'll put it in a specific form, and it's not like, it doesn't make any sense why they do that, but then you scroll further down in the paper and then they put it into that form because they're going to do something tricky with it, which I bet you is what they're probably going to do down here. So I don't know why they did this alpha t, but they're going to probably get into that. This is basically the same exact equation here. N xt, square root of alpha t, alpha bar, square root of 1 minus beta, x naught. So this is the original image. Here it's xt minus 1. 1 minus alpha t, sigma squared identity matrix. So sigma squared identity matrix, just the variance of the noise. A variational lower bound is then used to optimize the reverse diffusion chain. Probability, or p of theta gives you x of t minus 1 given x of t. So this is the actual diffusion model. P of theta is the actual diffusion model. Jesus Christ. All right. Kind of a sloppy example of GANs, to be honest. But TLDR, I feel like the most important part is the couple sentences up here, right? Is that fundamentally you just have this min-max game between two neural networks, the generator and the discriminator. The generator is taking a random noise, either uniform or Gaussian, and then it projects it into the actual image space, and then the discriminator is just taking that image, X, and trying to say, is this real or is this fake? And that's all you really need to know for GANs. To construct a diffusion GAN, we describe how to inject instance noise via diffusion, how to train the generator by backpropagating through the forward diffusion process. This is the more tricky part. I don't know how they're actually going to do that. And how to adaptively adjust the diffusion intensity. This just seems like the noise schedule. We further provide theoretical analysis illustrated with a toy example. Instance noise injection via diffusion. We aim to generate realistic samples xg. So x is the image, and then xg, I guess, represents an image that has been generated by the generator network, right? The generator is a neural net that maps a latent variable z. They're kind of redefining the stuff that they did up there, but okay, sure, we'll keep going. From a simple prior distribution, right? The distribution of the latent z's that get fed into the generator should be quote-unquote simple, so they say either Gaussian or uniform, to a high-dimensional data space such as images. The distribution of generator samples, xg of z, xg, which is sampled from g, which is takes as input z, and then z is sampled from a distribution, is denoted by pgx, Integral of pxg given z, p of z dz. So distribution of generator samples, right? So generator samples are xg, pg of x is the distribution over all those generator samples. And the whole point is that you want this pg of x to equal p of x, right? You don't want pg of x, which is the distribution over generator samples, to be the same as p of z, right? P of z is going to be a uniform or a Gaussian. These are just latent noise vectors, right? What you really want is you want this pg of x to eventually get as close as possible to your true image distribution, right? The image distribution of your actual images, right? Which is, I don't know, celebrity A images or whatever, right? The actual pictures of people's faces. To make the generator more robust and diverse, we inject instance noise into the generated samples by applying a diffusion process that adds Gaussian noise at each step. The diffusion process can be seen as a Markov chain that starts from the original sample x and gradually erases its information until reaching a noise level sigma squared after t steps. So, I mean, I know Markov decision processes from reinforcement learning, but Markov decision processes and reinforcement learning have a more precise definition. I think Markov chain might be just literally, let's make sure we know what we're doing. Markov chain is a Markov stochastic model describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. Okay, so basically you have a graph. So a graph, anytime you see little circles with these arrows connecting it, that's what's called a graph. This is a very common way of representing things in, I don't know, computer science or any kind of formal system. But basically the nodes are a state, and then traversing the nodes, right, you're going from state E, and here you're saying you have a 0.3 probability of going from state E back to state E, 0.7 probability of going from state E to state A. Right? So possible events here, you can either go back to E or you can go to A. There's a probability for each of the possible events. And if you take the same set of steps from the same starting place, you're going to end up at the same place, right? Which is part of the reason why I don't like the Markov decision process for reinforcement learning, because it has this assumption that the world is like this, right? It assumes that the real world has this property that if you start from the same place and you do the same things, you end up in the same place, which I don't think is true for the real world. But for the exact definition of a diffusion process like this, where you know exactly the noise that you're adding, this is a Markov chain, right? Because if you start from here and you add whatever 10 steps of noise, then you know exactly where you're going to end up. And if you do the same thing from the same image, you're going to end up at the same place, right? So that's largely what they're saying here. Gradually erases the information. You're gradually adding the noise. We define a mixture distribution that models the noisy samples Y obtained at any step of the diffusion process. So a mixture distribution, I guess here they're saying X is the image and it gives you Y. What is Y? Noisy samples Y. So Y is the X, but with some noise added. Obtained at any step with a mixture weight pi t for each step. Okay, so it sounds like they're going to be doing this similar to the idea of guidance sampling. Maybe not at all, but like, let's keep reading. Before I start making random conjectures, let me keep reading this. The mixture components are Gaussian distributions with mean proportional to x and variance depending on the noise level at time step t. So the mixture components, right, they have a mixture of Gaussians, right? So each component within this mixture of Gaussians is a Gaussian. So each of these is a Gaussian. Y given x and t. So here you have y given x, here you have y given x and t, so you're also given the time step. Proportional to x and variance depending on the noise level at time step t. Okay, so all they're saying here is that basically this mixture distribution Q depends on the image X and the time step T. We use the same diffusion process and mixture distribution for both the real samples and the generated samples. Okay, so you're not going to be using a different diffusion process for the generated versus the real images, which makes sense. You would want those to be the same, right? X is sampled from P of X. This is the real images, right? Here is the generated images. So you want P of X, which is a data distribution, and you want PG of X, which is a data distribution. You want those to be as close as possible, right? So if you took the KL divergence of P of X and PG of X, you want that number to be very small. The diffusion-induced mixture distributions are expressed as, here you go. So here you have X sampled from P of X, Y sampled from Q, Y given X, Q, which gives you Y given X, is this. You have pi T, which they said is the mixture weight, right? So you have a bunch of different weights depending on the time steps. You see how this pi T is dependent on the time step. Okay, so this is the Q, Y given X is basically just Q, Y given X and T, but you're multiplying each one of these by this weight, which depends on T, summing them over all T, and that'll give you Q. And this equation is basically the same thing as the above, except they put these little g's here, and the little g just means that rather than actually sampling it from the dataset distribution, you're just it's coming from the discriminator. Where Q, Y given X is a T component mixture distribution. So there's T total components inside that. That seems really intense. So you're telling me that if T equals 1,000, you have 1,000 different Gaussians? That doesn't seem right. The mixture weights are non-negative and sum to 1. Okay, good to know. Mixture weights are non-negative and sum to 1. Right, I guess here it's because they would want all of these. You wouldn't want pi of T to not sum to 1, because then this term here would depend on the time. The magnitude of this term would change as you increase and decrease the total amount of time steps T. And I think they said earlier that they're going to be changing the total amount of time steps T, the total amount of diffusion steps. So it makes sense that if you're going to be changing this capital T, you want the mixture weights pi of T to sum to 1. Are obtained via diffusion as in equation 1. So Q, Y given X comma T, which is this term here, and this term here, is equal to the N, which is the Gaussian distribution centered on Y, with this scheduled noise or scheduled variance that depends on the time step. Dude, there's so many terms here. What is Y again? Noisy samples. Y. Okay. So the noisy samples are basically just the X multiplied by the time step dependent noise. So this is just an elaborate way of saying the noisy samples are basically X plus whatever noise the Gaussian diffusion or whatever noise the diffusion process adds to them. And because the diffusion process is very specifically and formally defined here, you can know it's a quote-unquote Markov chain, right? Because you kind of know exactly what the amount of noise should be at a specific point in time. You can get the noisy sample at a specific point in time. Samples from this mixture can be drawn as T. So T is sampled from P of pi, discrete, so there's a discrete amount of these weights, mixture weights that depend on the time step that are summing up to 1. This is a discrete distribution, right? There's a limited set of those. And then here you just have the noisy sample. So if you want to sample from this mixture here, you basically need to pick a bunch of pi of t's, pick the t and the x, add the noise to that, and then you get the noisy image, which is y. By sampling y from this mixture distribution, we can obtain noisy versions of both the real and generated samples with varying degrees of noise. What's the whole point of doing the diffusion here? Like, I'm still not getting it. Like, really all they're doing is just adding noise to the original image and then adding noise to the image that comes out of the generator, and then just, that's it, right? So why do all this complicated diffusion process stuff? Like, why not just say, hey, we're augmenting the images before we feed them into the discriminator, right? The more steps we take in the diffusion process, the more noise we add to y, and the less information we preserve from x. We can then use this diffusion-induced mixture distribution to train from a time-step-dependent discriminator d that distinguishes between real and generated noisy samples. So time-step-dependent discriminator d. So this is the difference. So what I just said is, hey, why not just add noise to the image and the generated image, and then the discriminator is saying, okay, this is either the real image or the fake image. But here, the way that they're saying this, the discriminator not only has the image as the input, but it's also receiving the t, which is in some way basically how much noise there is. So the discriminator is aware of basically the amount of noise, because the amount of noise is also time step dependent. So maybe that extra little signal that you're giving to the discriminator there allows it to do something a little bit more nuanced, right? Maybe it starts to learn that when the noise is very low, it should be when there isn't a lot of noise and the time step is very close to zero, right? Whenever you're here, the discriminator learns to say, or learns to pay attention to the kind of high frequency features. So the texture and kind of edges, right, what would normally be at the base of kind of a convolution. I constantly make this analogy, but in a convolutional network, the stuff that's closer to the image, I call it the high frequency features, are things like texture. And then as you get higher up in the convolutional neural network, the features at the top are the more high level semantic features, also sometimes called the low frequency features. So maybe by giving the discriminator this time step, you're kind of telling it whether or not to use high frequency features or low frequency features, right? You're telling it, hey, discriminate based on the size of this person's head and the relative spacing between their eyes and like those kind of things, like high level features, versus if you're giving it a low time step, you're basically telling it, okay, you should be able to discriminate based on the texture, right? These high level features or high frequency features. So that's like something that I'm thinking about right now based on this paragraph. We introduced Diffusion-GAN that trains as discriminator and generator with the help of diffusion-induced mixture distribution. Diffusion-GAN trains as generator and discriminator by solving a min-max game objective. So this is the same V that we saw up here, right? So this is the min-max that we saw up here, except all they're going to do is they're probably just going to plug in these equations that they had from up here. Yeah, so this looks very complicated, but it's really just the same thing. It's just here you have the same discriminator, which is receiving the image or the noisy image y, and here you see it's also getting the time step t, and here you have one minus that, where here this is the real image with noise, and this is the generated image with noise, right? So yg is generated image with noise at some time step, and this is the real image with noise at some time step. And here is just a bunch of terms that basically are saying the expected value given these terms, right? So the expected value, this like fancy script E, applies only to this little part here in the square brackets. Everything else under here, this subscript over here, is just basically a kind of like a condition on this expected value. So, for example, the Z, which is the vector that is given to the generator in order to generate the image is sampled from some probability distribution here, P of Z. T, which is the time step, is sampled over some probability distribution here as well, P of pi here. Y of G, the generated image, comes out of this Q of Y given G theta of Z. So G theta of Z is the generator, right? The generator neural network, which is parameterized by theta, which are the actual weights of the generator neural network, and T. And then let's see what all these terms over here on this expected value are. You have X sampled from P of X. So this is your actual image data set. T from P of pi, so the same T here, right? Same two distributions for T, the time step. You have Y coming from Q, Y conditioned on X and T, which is basically the same here, right? You have this similar kind of situation, but note how Y versus YG, the only thing that's different here is this G theta Z. So this Y, right, this noisy image here is actually taking the real image X versus this Y over here, Y sub G, is taking the image that is generated by the generator here. Lots of terms here. Where P of X is the true data distribution, P pi is a discrete distribution that assigns different weights to each diffusion step. Discrete distribution that assigns different weights to each diffusion step is just another way of saying we have arbitrary kind of weights for each diffusion step 1 to T. Maybe they have an actual kind of theoretical choice for that, but it could just literally be like a dictionary in Python where step 0 is this, step 1 is this, step 2 is this, step 3 is this. So a discrete distribution that assigns different weights pi of t to each diffusion step could literally be a Python dictionary where the key is the diffusion step and then the value is just the value of this weight pi of t. And Q, Y given xt is the conditional distribution of the perturbed sample Y. So here they're saying perturbed, but it just means the image plus the noise. By equation 2 with Gaussian reparameterization. So this is a trick. So there's something called the reparameterization trick. And this is used in reinforcement learning, but reparameterization trick. Yeah. And what the reparameterization trick is doing is this is not at all any kind of interesting thing here. Let's see if we can find a better image. No, I don't know if we can find a better image, but my explanation of the reparameterization trick is that you can take any Gaussian and turn it into, you mean VAE? Variational autoencoder. Variational autoencoder is different than reparameterization. Reparameterization is basically saying that you can take a Gaussian with a certain mean and variance and turn it into a unit Gaussian that is offset, right? So it comes down to the fact that you can, and the reason people do this is because they want to like cancel out terms or like be able to basically pass the noise through, right? In order to make something differentiable, you can separate out the different parts of the Gaussian, make it a unit Gaussian, and then at that point it becomes easier to push the gradients through it. So the perturbation function here, y equals alpha bar, square root of alpha bar x plus 1 minus alpha bar sigma e. So where is that here? Here's the qy given xt. This is the mixture here. Where 1 minus blah, blah, blah equals is the cumulative noise at time step t, sigma, and e is Gaussian noise. So yeah, here's the point. So previously, right, the y here was a Gaussian distribution with these complicated means and variances here, right? But using the reparameterization trick, they pulled out the unit Gaussian here. So you see how this little e here, the sigma, is now a unit Gaussian. What I mean by unit Gaussian is a Gaussian that's centered on 0 and has an identity matrix for the variance, right? Which means it's just a pure Gaussian. So by doing that, they pulled out the Gaussian part of this y. So now this is going to be where they actually get the gradients to flow through it. The objective function in equation 3 encourages the discriminator to assign high probabilities to the perturbed real data and low probabilities to the perturbed generator data. So the discriminator, re-parameterized from diffusion paper. Yeah, it's re-parameterization is like everywhere. Like people use it in all different places for all kinds of different reasons. From kind of my history and kind of the way that I learned these things and the way that I kind of went through the field of machine learning, I was first introduced to it in the concept of reinforcement learning, where your policy outputs like a distribution over actions, and you use the re-parameterization trick in order to make in order to be able to push gradients into that policy. But I bet you that there's a million other ways to do re-parameterization and a million other reasons to do it. And if you go into, I don't know, like biology or any other kind of statistics field, they probably have other uses for this trick. It seems like here they're using it because they're probably going to want to push gradients on, or they're going to want to push gradients through the diffusion process into the generator, right? That's my guess. Okay, but here, the discriminator assigns high probabilities to the perturbed real data and low probabilities to the perturbed generator data, right? The discriminator, what the discriminator is doing is it's doing a classification problem. So the discriminator output is basically probabilities. It's kind of like a classification problem where you have cat versus dog. The output is whatever, 80% cat, 20% dog, 10% dog, right? So what the discriminator is outputting is probabilities. Or not really, it's outputting logits, and then those logits are being interpreted as probabilities. The generator, on the other hand, tries to produce samples that can deceive the discriminator at any diffusion step t. I mean, to me, I don't like this because it feels like it like anthropomorphizes what the generator is doing, right? Like, the generator is just a neural net. It's just a function approximator. This idea of it like deceiving, like there's deception isn't like an actual thing, right? It's just like the way, it's just a min-max objective, not a deception. Note that the perturbed generated sample can be rewritten as this. So similar again, re-parameterization trick. And this means that the objective function is differentiable. There you go, boom. That's the whole point. So this whole re-parameterization, the whole point of it is that you can now differentiate through it, which means you can do the chain rule, which means you can push gradients, right? Because backpropagation, which is the way that you change the parameters of a function approximator, aka a neural net, in order to better perform your task, which is the whole concept of learning. The way that you quote-unquote learn is by updating the weights. In order to update the weights, you need to do the chain rule. In order to do the chain rule, everything in your function approximator must be differentiable. So anytime you're doing any kind of machine learning, you need to use things that are differentiable in order to do backpropagation and gradient descent. So in a lot of kind of like, for example, nerfs, right? Like the cool part about nerfs is that someone came up with a specific formulation of like 3D space and rendering stuff from 3D space in a way that's differentiable, right? The cool part about diffusion models is that someone came up with a way to kind of add and remove noise and blah, blah, blah in a way that's differentiable. So most of like deep learning and kind of finding interesting, cool, novel things in deep learning is about being able to find some specific formulation of the process where everything is differentiable so you can push gradients through it. Okay, the objective is similar to the one used in the original GAN, except it involves diffusion steps and the perturbation functions. We can show that this objective function also minimizes an approximation of the Jensen-Shannon divergence. I don't know what this is, but Shannon is the Shannon entropy. This is the information theory guy. And Jensen-Shannon divergence between true and generated distribution makes me think that this is some kind of distribution metric. So kind of like a KL divergence. Let's see, Jensen-Shannon divergence. Yeah, it's basically that. So Jensen-Shannon similarity between two probability distributions based on the KL divergence. Okay, so Jensen-Shannon divergence is basically a variant of the KL divergence. And in fact, here you go. The KL divergence is the distance between P, this distribution, and Q, this distribution. And the JSD is 1/2 PM and 1/2 QM, where M equals 1/2 P plus Q. Ah, okay. So now I understand. So one of the problems with the KL divergence is that the KL divergence is not symmetric. Is that the KL divergence between a P and Q, right, where P and Q are both data set distributions, is different from the KL divergence between Q and P. So maybe the whole point of this JSD, right, and the way that they're doing this, right, where it's like 1/2 of P versus this combined and then 1/2 of Q versus the combined, maybe the whole point of doing that is so that it is symmetric, but I don't know. Maybe one of you guys knows the reason that people use this one as opposed to KL divergence. But what are they doing this for? So DJS, right, this distribution metric here, they're doing it in between P of Y given T and then P of G of Y given T. So the distribution of noisy images that are generated should be the same as the distribution of images, of noisy images that are not generated, that are just sampled from your distribution. The JS divergence measures the dissimilarity between two probability distributions, and it reaches the minimum value of 0 when the two distributions are identical. Okay, so ideally your generator is generating images that are basically exactly from the distribution of real images. Those distributions are the same, and then therefore this DJS term should be 0. So you want to minimize this term. The proof of equality in equation 4 is given in Appendix C. A natural question that arises from this result is whether minimizing the JS divergence between the perturbed distributions implies minimizing the JS divergence between the original distributions. Yeah. This is a little weird, right? Where you don't necessarily care about these noisy images Y, right? What you really care about is the not noisy images X, right? XG, right? X is the actual image. Y is the image plus noise, right? So you see how YG here is image plus noise, but what you really want is XG, which is the actual image. So you want the distribution over the actual images, right? P of X and P G of X, right? So you want the X's, the distribution over the X's to be the same, not the distribution over the Y's to be the same. And that's what they're saying here, is they're saying, hey, actually, we admit that it's not entirely clear that minimizing this this difference between these two distributions here should be the same as minimizing the difference between the original kind of image distributions, not the noisy ones. But the noise that they're adding is just, it's all just kind of variance of Gaussian noise. So I don't know, that seems like it should work. But they provide a theoretical justification. So I don't think you necessarily need the theoretical justification here, but whoever wrote this paper is obviously very math heavy, like just the amount of math that they've put in here, and like every single section has had a ton of math. So when you have a very math heavy paper, of course, that type of person is exactly the type of person who's going to want to provide theoretical justifications, right? They're chomping at the bit to write more math. Adaptive diffusion. Let me take a quick little sip of coffee here and I'll be back. So if you guys have any question, let me know. I feel like I'm just kind of blasting through this paper, but I don't know if you guys are just not understanding or if I'm just getting things wrong or if people just don't care, but let me know if you guys disagree with anything or if you guys have any questions or if you're confused about anything. With the help of perturbation function and time step dependency, we have a new strategy to optimize the discriminator. We want the discriminator D to have a challenging task, neither too easy to allow overfitting the data nor too hard. So this is the hard part of GANs, right, is that the discriminator and needs to be kind of in tandem with the generator. They need to be kind of getting better at the quote-unquote same rate. Therefore, we adjust the intensity of the diffusion process, which adds noise depending on how much D can distinguish between them. Okay. This is very clever. This is kind of the new... This is actually a very good point, right? This kind of sounds like score-based generative modeling with multiple noise perturbations. Yeah, I don't know that exact paper, but I like this idea, right? So when you're training GANs, right, you have to keep the generator and the discriminator at the same level. If the discriminator starts having a very hard time distinguishing between the things, it's not going to be able to pass a meaningful signal into the generator. So it seems like what they're saying is like, hey, you can actually use the intensity of the diffusion process as a kind of handicap for the discriminator. So if the discriminator is getting too good, add more noise. If the discriminator is having a really hard time, take away some of the noise. So it adds like an extra dimension to be able to kind of like make the discriminator either catch up or slow down. So that's kind of cool. I really like this idea. When the diffusion step T is larger, the noise to data ratios are higher and the task is harder. Yeah. We use 1 minus alpha bar T to measure the intensity of the distribution of the diffusion, which increases as T grows. To control the diffusion intensity, we adaptively modify the maximum number of steps T. So I guess if you have a lower amount of steps T, each individual step is going to add more noise. So if you have 1,000 steps, each individual step is only adding a very tiny amount of noise. But if you have, I don't know, 3 steps in some extreme case, then the amount of noise that you're going to add is significant. But I doubt they're going to be doing 3 to 1,000 steps. It's probably like 10 steps versus 100 steps versus 1,000 steps or something like that. Our strategy is to make the discriminator learn from the easiest samples first, which are the original data samples, and then gradually increase the difficulty by feeding it samples from larger T. To do this, we use a self-paced schedule for T. What is self-paced? Which depends on a metric RD that estimates how much the discriminator overfits to the data. Okay, so they're going to be changing the number of time steps T right here. So T is going to be a function of R of D, which is this metric, which we're going to look at in a second here, minus D target, which is going to be some kind of hyperparameter. They're probably going to pick that number here, this D target, and then C, which is probably another hyperparameter. Yep, here it is. Okay, C is a constant. So you have, this isn't necessarily great. You have 2 hyperparameters here that are picked. So D target's probably picked, and then C is also probably picked. And then here, sign just means negative or positive. So depending on whether or not your RD is above target or below target, you're basically going to add or remove C time steps from it. R of D here, which is the actual metric. This is the expected value with Y and T sampled from a probability over Y and T. So this is the noisy images and the time steps T. Oh my God, fuck. I saw that click coming. Get back up here. Okay, here we go. Nope. Yep, here we go. d of phi, so this is your discriminator, of course, a neural net parameterized by the phi parameters, right, which are just a bunch of weights. Your discriminator is going to take the noisy image, and it's going to take the time step, and it's going to output a probability of whether or not this image is real or it's fake, right? So if the discriminator is very confident about its predictions, right? If it's very confident that this image is real, if it's very confident that this image is fake, it's going to be basically 1 or 0, right? So if the discriminator is outputting 0.5, that means that it's not confident at all, right? It's kind of like very similar to how whenever you have an object detector and you can look at the confidence of each of the bounding boxes, right? You can do the same thing with the discriminator because it's doing classification, and because the output of the classification is a logit, which you can interpret as a probability. You can also interpret that logit as kind of a confidence score, right? So they're basically saying if the discriminator is very confident, then we're going to give it more time steps t, so that, or we're going to give it, if the discriminator is more confident, then we increase the difficulty by giving it more time step, a larger t, which means more time has passed, which means there's more noise. Okay. So that's pretty much all this means, is that they're looking at the confidence of the discriminator and adding or removing noise from that. I think I have maybe one problem with this, is that I don't know if the confidence of a classification model is necessarily a good proxy. I feel like perhaps the confidence might be misleading, and it might be, you know, like sometimes the confidence can be misleading, but I don't know, maybe it just kind of works out and it doesn't matter. But that would be my only kind of feedback there. We have two options for the distribution P of pi that we use for the sample T for the diffusion process. So T is the actual time step that's coming from a distribution P of pi. There's two different ways, so two options. So they pick either one of these two things. So you either have a uniform distribution, uniform over all T, or priority, which is 1 over the sum from t equals 1 to t of t. Okay, so the priority option, which is this one, gives more weight to larger t, which means the discriminator will see more new samples from the new steps when t increases. So larger t means that there's more noise. So the priority option gives more weight to larger t. So priority weight is going to say, don't bother looking at these, look at these over here, the ones that have a bunch of noise on them. This is because we want the discriminator to focus on new and harder samples that it has not seen before, as this indicates that it will be confident about the easier ones. Note that even with the priority option, the discriminator can still see samples from smaller t, because Q of y given x is a mixture of Gaussians that covers all steps of the diffusion chain. So they're saying this isn't necessarily 0, so even if you're using this priority sampling technique, you're still going to occasionally sample things that are here. You're not always going to necessarily be sampling things that are there. To avoid sudden changes in T during training, we use an exploration list TEPL. Oh my God, this like so much complexity in this paper. This paper has all the complexity of diffusion papers, all the complexity of GANs, and then they add additional complexity on top of that. So maybe another thing that I don't necessarily like about this paper is that it's just way too complex, right? It's like there's something to be said about simple techniques that are easy to understand, easy to identify, easy to explain. Like transformers are simple, right? Stacking a bunch of transformers and training it with a next token prediction, very simple. Diffusion models, also kind of simple. So I think there's this kind of push and pull in research where something will work and then someone will take that. I think it's not. I don't think they're doing it on purpose. I think that it's like the way that research works. It's like someone comes up with a new concept, and then people will take that new concept and add a little new thing on it, and then somebody will take that and add something else to it, and add something else to it, and eventually you added so many things to this concept that it becomes a little bit too intense, too hard to understand, too hard to add one more thing on it, right? The cost of adding one additional system to it gets higher and higher. So eventually, 2 years, 3 years from then, somebody will come up with a simpler abstraction that gets rid of all this complication, right? So I think the problem with this type of paper is that even if it works well, adding one additional thing to this is going to be very complicated because it's already very complicated. So this is almost like peak complexity, right? Where it's like, you can imagine this paper, but you have like some fancy noise sampler, right? Imagine this paper, but you're using a quantized latent that is being used for the GAN, right? It's like you can keep adding more stuff to this paper, but it's like it's going to get to the point where it's like going to be impossible for anybody to even re-implement this because there's just so many moving parts. So this is like kind of getting to that limit where it's just like there's too much crap going on right here, right? Like exploration list, right? That contains t values sampled from p of pi. We keep TEPL fixed until we update t, and then we sample t from TEPL to generate noisy samples. So not only are they choosing the t from either one of these two kind of distributions, but then also they're keeping this kind of list, almost like a table of previous values of t, and then referencing that table. So it gets getting a little complicated. To better understand the theoretical properties of our proposed method, we present two theorems that address two important questions about the use of diffusion-based instance noise injection for training GANs. We're getting theorems. The proof of these theorems are deferred to Appendix B. The first question is whether adding noise to the real and generated samples in the diffusion process can facilitate learning. So I don't feel like you need to prove that. I feel like that's almost common sense, right? I feel like there's more than enough intuition that if you take image distribution and you add noise to that image distribution, you will get a better object detector, a better classifier, a better whatever you want, because you're basically making the model more robust to noise and making it more data efficient, because you're also basically every single paired example of an image and some kind of learning target is being amplified because you're adding noise to it. So to me, adding noise to the real and generated samples, that's just basic machine learning. I don't feel like you need to necessarily prove that. Data augmentation works. The second question is whether minimizing the JS divergence between the joint distributions of the noisy samples and the noise levels can lead to the same optimal generator. So this one is a little bit less clear, but I think the same thing. I think it is largely the same, right? It's, hey, rather than minimizing the JS divergence between the actual image distribution and then the generator image distribution, right? The PGX versus PX. They're saying, hey, is it the same if we minimize the JS divergence between PYT and PGYT, right? Where now it's a distribution over the noisy images, and then you're also feeding it the time step T. So these two distributions aren't necessarily the same as the original image distribution and the generated image distribution. But I feel like they're close enough that it should be fine. Yeah, PX and PGX. We proved that for any notion of noise level T in any choice of convex function F, the F divergence between the marginal distributions of the noisy, real, and generated samples is a smooth function that can be computed and optimized by the discriminator. Okay, I don't really know what F divergence is, but basically they're saying that these two distributions here, the difference between them is smooth. So it should be fine. You should be able to basically follow gradient descent to get to the answer that you want. Right? Smooth, there's no discontinuity in that space. This implies that the diffusion-based noise injection does not introduce any singularity or discontinuity in the objective function of the GAN. Yeah. The JS divergence is a special case of F divergence. So I guess F divergence is probably the simplest, kind of most basic, most high-level explanation, or most high-level version of comparing two data set distributions, or two distributions. Let's see. F divergence. The F divergence is always positive. The F divergence is a function that measures the difference between two probability distributions. Okay, so F divergence is a family of all possible things that include KL divergence, this whatever Shannon divergence that they're doing here, the JS one. So F divergence is just any function that measures the difference between two probability distributions. The JS is a special case. Okay. Theorem 1, valid gradients. So this is an actual little theorem here. Is this even worth me reading here? Let P of X be a fixed distribution over X and Z be a random noise over another space C. So denote G of theta maps from Z to X, right? So you could think of a function as basically taking a point in some space and converting it into a point in a different space. And that's what they're showing here is they're saying that this function here, G of theta, which is the generator, right, parameterized by theta, takes points from this space Z, which is the noise vector that gets fed into the generator, and maps them to these points X, which are points in your image space. With parameter theta and input Z and PGX as the distribution of G theta Z. Let Q y bar X T equals that, where alpha bar T in 0 to 1 and sigma greater than or equals 0, so this is variance greater than 0, and alpha bar, which is the schedule with which they change the variance of the noise over the course of the diffusion process, is bounded by 0 and 1. If function G theta is continuous and differentiable, which it is because you're picking a neural net which is specifically chosen to be differentiable, the F divergence df y given t and qg y given t is continuous and differentiable. Okay, so basically this is a very long way of saying that if the generator, which is a function that maps from z to x, is continuous and differentiable, then the F divergence, which is any metric, any function that compares two distributions, is also continuous and differentiable. So I don't know. We'll just take that as is. Theorem 1 shows that with the help of diffusion noise injection by Qy given xt, are same space the whole x. So this is the actual data set, the actual image space for the actual data set. Continuous and differentiable. Then one natural question is, what if blah keeps a near constant value and hence provides little useful gradient? So this is the mode collapse, right? So what if the let me actually use the right term. What if the F divergence of JS, this JS F divergence, ends up giving you the same value for this point, for the difference between the generated distribution and the normal distribution, and the not normal, but the non-generated one, so the actual distribution? By injecting noise through a mixture defined over all steps, there is always a good chance that a sufficiently large T is sampled to provide a useful gradient. So this is a little bit more intense here, right? Theoretically proving that there is always a good chance that a sufficiently large t is sampled to provide a useful gradient. Like, there's a lot of terms there that are a little bit dicey, right? Like, always a good chance, useful gradient. Like, those two terms are a little bit too fuzzy for me to feel like you can theoretically prove it, which I think is why they're saying we empirically show. So here they're theoretically proving to you, like with actual math, that the continuous and differentiable property is maintained. But here they're saying we can't actually prove this, and maybe they tried to prove it and it didn't work out. But here they're just saying, okay, we can't theoretically prove it, but we can empirically show it. And empirically show it just means that, hey, we're going to try 5 different examples, we're going to plug them in, and all of them are going to work, so therefore we empirically showed that this statement is correct. All right, we use the same simple example to illustrate our method. Let x0z be the real data and xg phi or theta z be the data generated by a one-parameter generator, where z is a uniform random variable in 0, 1. Okay, so they're basically choosing some toy distribution here. Rather than using the actual image distribution, they're going to use a toy distribution, which is basically just 0 to 0 to 1, and then theta to 0 to 1, right? So this is just like a generic one-dimensional distribution. The JS divergence between the real and the generated distributions is discontinuous, right? So this function is also discontinuous, though. It is log 2 when theta equals 0 and 0 otherwise, so it does not provide a useful gradient to guide theta towards 0. I'm a little confused here. I think the reason this is discontinuous is because it's bounded, right? It goes from 0 to a specific number, but outside of that, it's basically undefined. So when you take the JS divergence between these two functions, which themselves are discontinuous, the JS divergence is also going to be discontinuous. Maybe. That's kind of what I'm interpreting, but I don't know for sure. If you guys can help me out there, that would be great. We introduced diffusion-based noise to both the real and the generated data. The noisy data have supports that cover the whole space, and their densities overlap more or less depending on the diffusion step t. In the second row, we plot how the JS divergence between the noisy distributions varies with theta for different t values. The black line within t equals 0 is then the original JS divergence, which has a discontinuity at theta equals 0. As t increases, the JS divergence curves become smoother and have non-zero gradients for a larger range of theta. However, some values of t, such as t equals 200, still have flat regions where the JS divergence is nearly constant. To avoid this, we use a mixture of all steps to ensure that there is always a high chance of getting informative gradients. For the discriminator optimization, the optimal discriminator is under the JS divergence is discontinuous and unattainable. The toy example inherited from this first row plots the distributions of data with diffusion noise injected for t. The second row shows the JS divergence and the optimal discriminator value with and without our noise injection. Okay, so the toy example has a x, right? X is the actual. What is y? What is this y value here? They never did. Y is the noisy. Okay, so y is the noise image, or the noisy, in this case, one-dimensional number. And then x is the actual number. So this is without noise, and this is with noise. So at time step t equals 0, right? Time step t equals 0 means there's no noise. So therefore, x should be the same as y, which I guess is what you're seeing here. don't know why there's multiple values of y for x. Because the noisy data but then as you go more time steps, right, as you increase the number of time steps, right, here at t equals 600 you have a bunch of noise. So here at t equals 600, x and y are no longer kind of up and down. It's just kind of becomes more and more noisy. The toy example plots the distributions of data with diffusion noise injected for t. Second row shows the JS divergence and the optimal discriminator value. Okay, so JS divergence here, which is how different the two distributions are. And again, I think they said 0 means they're the same. Maybe they complicated in order to limit how many people could understand this paper to make it exclusive. Probably not. I don't think people maliciously overcomplicate things. I think they're genuinely trying to make it as easy to understand as possible. I think it's just a complicated concept that they're trying to give you here. But largely what they're trying to show you here, right, is that this DJS, right, this distance between the two between the two distributions, you're going to be taking the gradient with respect to that, right? At the end of the day, they're taking the gradient with respect to that difference here, right? They want the probability distributions to be the same between the real image and the generated image, right? And if you're taking the gradient with respect to that, you would basically, you want these, you want this, right? Because the way that the chain rule and kind of backpropagation works, you're effectively finding the kind of slope and then traversing down that slope, right? Everybody loves the kind of like the ball on the hill deep learning analogy, right? Where really what you're doing when you're optimizing a neural net is you're kind of rolling a ball down a hill where the hill is defined by the loss landscape, right? The loss landscape is another term that people use. So here in this toy example, the loss landscape is basically just one-dimensional here, right? So you can see that the loss landscape for time t equals 0 is very sharp. So if you start here, your gradient step might take you here in this direction, and then it might take you here in that direction, it might take you here in that direction. It's like if you put a ball right here, it's not going to roll down into this minima, right? It's just going to sit there. If you put a ball here at the t equals 500, it is going to roll down. So what they're fundamentally showing you here is that by increasing this t, right, all the way from t equals 0 to t equals 800, the landscape is becoming increasingly more and more kind of easy to roll this ball into the little local minima, right? Because at the end of the day, you want your ball to roll to the middle of this thing right here where the distributions are identical and the DJS is 0, right? Because if DJS is 0, it means this distribution here, QYT, is the same as the distribution here, QGYT. Optimal discriminator value D star. So the discriminator, right, is performing classification. So it's outputting a confidence or a probability, which you bound between 0 and 1. So if it has a very high confidence versus a very low confidence, right? And I think that's kind of what they're showing you there. Optimal value for discriminator. So I don't know what the curvature here means. I guess maybe here what they're saying is that whenever the time steps are small versus the time step is big, whenever there's more noise, the optimal value for the discriminator for any given x is like more similar. I guess what they're saying here you can have an optimal value between 0.75 and 0.25. The confidence doesn't matter as much. But when you have a low time step, which means there's not a lot of noise, the optimal value is either 0 or 1. I don't know. I don't really fully understand this one here. I kind of understand this. I don't really understand this, and I don't really understand this. But, okay. The optimal discriminator changes with t. A smaller t makes it more confident, and a larger t makes it more cautious. Thus, the diffusion acts like a scale to balance the power of the discriminator. This suggests that the use of a differentiable forward diffusion chain that can provide various levels of gradient smoothness to help the generator training. Yeah, I mean, I see what they're saying. I see what they're kind of getting at, where they're saying, hey, it's actually great. This is the thing that they put here, which was actually really cool, right? We adjust the intensity of the diffusion process depending on how much D can distinguish them. I like this idea, but I don't feel like you need to have the diffusion model in here, right? I feel like you could have just the noise added to the image can just depend on the confidence of the discriminator without necessarily having to use this diffusion model in there, right? I feel like the diffusion is almost like a distraction. It seems like you should just be able to add or remove more noise depending on the discriminator confidence directly. Why have all this extra stuff where the noise is part of a discriminator process or part of a diffusion process, right? That seems like unnecessary. It seems like they should just be adding in noise and removing noise based on the discriminator confidence, and they could just skip all the diffusion part. Like, let me see this paper that you recommended here, score-based generative modeling with multiple noise perturbations. Here we go. Score-based generative models are gaining lots of traction, blah, blah, blah. It has been known that denoising autoencoders are equivalent to score matching. In this project, we propose that it's possible to extend to denoise multiple noisy samples of an image together and get a better score estimate. We experiment this idea on some popular image data sets and show that denoising model can be trained quicker with lesser error as we increase the number of samples. Yeah, so this is, you're taking the actual image, then you're taking a bunch of noisy versions of that image, denoising them, and using that to get a new image. We claim that using multiple samples instead of one gives our score matching model a more sophisticated understanding of the true data distribution. Right, so this is basically the same concept, except instead of taking noise that is basically, hey, you have this image and let's add noise that's kind of in the same distribution of the image, but it's just kind of like moving the image slightly within that distribution. Let's take noise that is being added by a discriminator or by a diffusion process. Like, the more I look at this, the more I feel like the reason they're doing this is they just wanted to combine the diffusion models and GANs just to have that in the title, because GANs were popular and they wanted to show that GANs and diffusion models can be combined, but it just seems like unnecessary. Okay, Theorem 2, non-leaking noise injection. Given x and y and xg and yg, transition density. Given certain q, if y could be reparameterized into this, where p of e is a known distribution and both f and h are one-to-one mapping functions, then we could have py equals pgy. Do you still read the research paper, or do you just extract the juice by using ChatGPT? Yeah, I mean, you're not wrong, Ankit. I could probably stop reading these papers and just have ChatGPT read them for me. You know, maybe I'm a little bit outdated by reading them manually, but I don't know. Maybe I'm just in denial that ChatGPT is just going to be able to do this at much better than I will, you know? Because why would people watch this video if they can just copy-paste this paper and feed it into ChatGPT, and GPT explains it way better than I do, which is probably the case. I don't know. To answer question B, we present Theorem 2, which shows a sufficient condition for the equality of the original of the augmented data distributions. Finally, they're using the word augmented, right? But all they're doing is they're taking the image distribution and augmenting it, aka adding noise. The function f maps each x to a unique y. The function h maps each sigma to a unique noise term, and the distribution of sigma is known and is independent of x. Under these assumptions, the theorem proves that the distribution y is the same as the distribution of yg, if and only if the distribution of x is the same as the distribution of xg. I mean, that seems pretty obvious. If the distribution of the images is the same as the distribution of the generated images, then the distribution of the images plus Gaussian noise is the same as the distribution of the images generated plus Gaussian noise, as long as the Gaussian noise is independent of x. Is the noise independent of x? It is. I think it is. We take y condition on t as the y introduced in the theorem, then for all t fits the assumption made. By minimizing the divergence between q and qg, which is the same as minimizing the divergence between p and pg, we are also minimizing the divergence between px and pgx. This implies that the noise injection does not affect the quality of the generated samples, and we can safely use our noise injection to improve the training. This was almost like a conflicting statement. We propose Diffusion-GAN can be related to previous works on stabilizing the GAN training, building the diffusion generative models, and constructing differential augmentations for data-efficient GAN training. A detailed discussion on these related works is deferred to Appendix A. We conduct extensive experiments to answer the following questions. Will Diffusion-GAN outperform state-of-the-art GAN baselines on benchmark datasets? Will the diffusion-based noise injection help the learning of GANs in domain-agnostic tasks? Wonder what they mean there. Will our method improve the performance of data-efficient GANs trained with a very limited amount of data? For sure. You're basically doing augmentation. Image generation results on benchmark datasets. Ooh, these are not good datasets. CFAR10, Celeb A. CFAR10 is basically a joke. It's tiny-ass little images. We're talking 32 by 32 images. Celeb A, also very tiny dataset, 64 by 64. I feel Elsun, these are a little bit better, right? These are 256 by 256, so those images are a little bit more meaningful. Here they're comparing the Frechet inception distance, which is basically just you're feeding these images into InceptionNet, I'm pretty sure, and then you're looking at the distance in the embeddings that are the last layer of the InceptionNet. Let me make sure before I bullshit that. Frechet inception distance. Unlike earlier inception score, it's a Frechet distance over, where it is inception score. Yeah, so the score is calculated based on the output of a separate Inception v3 image classification model. So you take this Inception v3 image classification model, you feed the two images of CFAR10 in there, right? One that's not generated, and then one that is generated. And then you compare the distance between the little embedding spaces for those. But there's a lot of problems with that because the embedding space of a pre-trained Inception 3 image classification model is not necessarily like some kind of like secret like true mapping of the universe, right? It's like there's all kinds of biases and issues with the embedding space of a pre-trained Inception 3 image classification model. We need to make a new Frechet inception distance that uses the distance in clip space, or the distance in Dino V2 space, or the distance in image bind space. I feel like those might be more interesting than FID. We need to redo FID. Okay, but here they're comparing diffusion style GAN to style GAN and a couple different variants of style GAN here. And I don't know, the numbers seem not that necessarily impressive. I guess they're a little bit better. They're like very similar though. Oh my god. Holy shit. Stop. Stop it. Stop it. All right. We measure image quality using FID. We measure using 50K generated samples. The number of real images. All models are trained with 25 million images to ensure convergence. I think they probably mean 25 different steps, right? They're probably using the same images over and over again. There isn't 25 million images in Celeb A. We further report the improved recall. We build diffusion GANs based on the code of style GAN 2, projected GAN, blah, blah, blah. That's also why style GAN was very popular as a baseline, because the code was released and because you could use it. So a lot of GAN papers compare to style GAN. We empirically find T in the discriminator could be ignored by simplifying the implementation, minimizing the modifications to projected GAN. In the following experiments, we train related models with their official code. We run all of our experiments with either 4 or 8 NVIDIA V100, so that's how old this paper is. Comparison to state-of-the-art GANs. We compare diffusion GANs with a state-of-the-art GAN backbone style GAN 2. To evaluate its effectiveness, we compare it with both style GAN 2 plus diff-aug. So diff-aug is, I guess, diffusion augmentation. Is that what diff-aug is? Differentiable augmentation for data-efficient GAN training. This is not. Diffusion augmentation. Various types of differentiable augmentations. What's an example of a differentiable augmentation? Yeah, I mean, this is basically the same thing here. Diff-aug applies the augmentation T to both the real sample X and the generated output G of Z. So the image that's coming out of the discriminator and the original image X, you apply the same augmentation T to it, right? They're taking the real image X, they're applying the augmentation T. Let me make this a little bit bigger so you guys can see. And then the discriminator has to discriminate between those. What is the actual differentiable augmentation that they're using? They don't even tell you. Qualitatively, these generated images are all photorealistic and that have good diversity, ranging from low resolution to high resolution. Randomly generated images are found in Appendix K. So randomly generated images, what that means there is that you're starting with a noise vector z, right? The way that GANs work, you feed the generator a vector z, and then the generator is generating an image, but it's conditioning it on this original little noise vector z, which is actually very similar to how when you do inference with a diffusion model, you're starting from a noisy, usually latent vector, but it's the same kind of idea. You're starting from noise and then generating the image out of that. It's just that diffusion models are removing the noise iteratively, but GANs are basically taking that noise and instantly turning it in one inference step into an image. So okay, from the data augmentation, we observe that diffusion-style GAN v2 always clearly outperforms the backbone model across various data sets, which empirically validates our theorem. By contrast, both ADA and diffaug could sometimes impair the generation performance on sufficiently large data sets. This is possibly because the risk of leaking augmentation overshadows the benefits of data augmentation. I don't know, I think it's probably like a model capacity thing where if it goes back to what we were talking about in previous videos, where you have this fundamental relationship between the size of the model and the size of the data set. And if you have a very big model and a very small data set, the model is going to overfit on the data set. So augmentation techniques are going to be very useful because they're basically artificially increasing the size of the data set so that the model doesn't overfit as much on the data. But if your model is small compared to the size of the data, augmenting the data set might even make it potentially worse, because now your model has even more has even less capacity relative to the size of the data set. Randomly generated images from diffusion trained on CFAR10. So yeah, I mean, CFAR10, 32 by 32 images, like, I don't know, those look good to me. FFHQ seems like it's basically much higher quality randomly generated images. So this is basically this person does not exist, right? You're taking some random point in the Z vector, aka noise space, and then just getting an image from that. So you're basically randomly interpolating between all the different images in the original FFHQ dataset. And all of these look pretty good. One thing in like the original GAN papers was the teeth would be weird, would be one way to usually tell. It's like, for example, the teeth would be like centered, but here all the teeth are kind of symmetrically aligned. Other things here to notice, like you see how the glasses here are not the same size. Like this lens is smaller than this lens, so a little bit of mistakes there, a little bit of weirdness going on here around his head. Training progress. This is unusual. They call it million of real images, but I bet you it's a lot of the images are actually the same, and they're basically using the same image and then just adding noise to it. So to me, this is more like steps, like training steps. T is the T schedule, so the total amount of diffusion, which is basically just how much noise they're adding, and you can see how if you have more steps, aka more noise, no, okay, I'm wrong. T is not chosen. T is defined. So T is automatically chosen by the model itself. So depending on how good the discriminator is, it'll start increasing the T, right? That's what we saw. So this is basically telling you they were calling it self-supervised or whatever they self let me see the exact terminology they used here. Not adversarial, adaptive. Self-paced schedule.
self-paced is the term they use. But basically what they're referring to is that the t is going to change as a function of the discriminator over time. So as you train, the discriminator is either going to become better or worse, and you're going to be adapting this t. So you see here how for this, for example, this red line here, it starts very, very low, and then it gets a little bit higher, and then it goes back to being low. I don't know what you would want. I don't know what the actual like desired behavior for this t would be. It seems like there's basically two different modes here. There's this kind of like mode where it starts low, goes high, and then goes back low, and then there's this mode where it starts low and then just stays high. Here you have real and generated images. So this is the discriminator. This is the output of the discriminator. So the output of the discriminator is a classification model. It can, the raw output. So up until now, usually they're showing you the softmax output. So the softmax is going to be between 0 and 1, but here it's not 0 and 1, which is telling you that this is before the softmax. So this is like the raw logit, and you see here how negative means the discriminator thinks it's a generated image, and then blue and then positive means it thinks it's a real image. And you can see here how over the course of training it gets more and more confident. These lines kind of slowly diverge away. But there's still a bunch of overlap. You see there's still overlap of the red area into the positive and the blue area into the negative. We see that t is adaptively adjusted. Yep. T does change over time, but I don't know what exactly do you want? What is the like desired behavior of t? That's kind of what I'm asking. The second panel shows that trained with a diffusion-based mixture distribution, the discriminator is always well behaved and provides a useful learning signal for the generator, which validates our analysis. So I guess what they're saying here is that this blue line doesn't kind of like jump around. It always stays above this 0, and it kind of slowly moves away from the 0, which is the smooth, aka well-behaved behavior that they want. Memory and time costs. Generally speaking, the memory and time costs of Diffusion-GAN are comparable to those of the corresponding GAN baseline. More specifically, switching from ADA to our diffusion-based augmentation, the added memory cost is negative, the added training time cost is negative, and the added inference time cost is 0. So added inference time cost means that really you're only doing this diffusion stuff when you're training. You're only adding and removing noise when you're actually doing the training, so it doesn't change whenever you're doing inference. Whenever you're doing inference, you just use the GAN as normal. Added memory and added training time is negative. They're comparing to this other thing here, this ADA, which probably is just not as good. But compared to a normal GAN, this is obviously going to take slightly longer to train because you have to perform that augmentation, the actual adding the noise and so on. For CFAR10 with 4 NVIDIA V100s, the training time is around 8 seconds, 9 seconds, and 9.5 seconds. To verify whether our method is domain agnostic, we apply Diffusion-GAN onto the input feature vectors of GANs. We conduct experiments on both low-dimensional and high-dimensional feature vectors for which commonly used image augmentation methods are no longer applicable. We conduct experiment on the popular 25 Gaussian generation task. So I guess this is a task where you have a dataset distribution that is basically 25 random Gaussians generated by a mixture of 25 two-dimensional Gaussian distributions. So you're trying to predict that distribution, right? Rather than trying to predict an image distribution, which is difficult to understand as a human, you have a two-dimensional toy distribution, which is just a mixture of 25 Gaussians. We train a small GAN model whose generator and discriminator are both parameterized by a multi-layer perceptron with 2 128-unit hidden layers and leaky ReLU nonlinearities. So normally your generator and discriminator are going to be a little bit more complicated, especially if they're in image modality, right? So here the generator and the discriminator, they're consuming a image, so they're going to have a convnet or something like that in it, you know. But yeah, this generator and the discriminator. But here, because they're just doing it on this toy problem that is 2D, the generator and the discriminator, they're just going to use MLPs, which are basically just fully connected little neural nets. And these are pretty tiny too, 228 unit hidden layers. The training results are shown in Figure 5. We observe that the vanilla GAN exhibits severe mode collapse, capturing only a few modes. So if they just use a GAN as is, they get this mode collapse where its discriminator departs, which basically means that out of the 25 Gaussians that they know are underlying this dataset distribution for the toy dataset, the GAN only learns to kind of pay attention to a couple of those, right? Only a few of these 25 Gaussians. This implies a strong overfitting of the discriminator so that the discriminator stops providing useful learning signal for the generator. However, Diffusion-GAN successfully captures all of the 25 Gaussians and the discriminator is under control to continuously provide useful learning signal. We interpret the improvement from two perspectives. First, non-leaking augmentation helps provide more information about the data space. Second, the discriminator is well behaved given the adaptively adjusted diffusion-based noise injection. Little misspelling here, GRUD truth. This should be ground truth. So you see here you have a two-dimensional space with 25 Gaussians, right? So you have 25 little Gaussians in this space. So ideally, what you should be able to say is you should be able to say, okay, any point that is here is going to be fake, and all the points that are here are going to be real, right? So as a human, I can instantly tell that, for example, this right here, these should be fake points. So this is already wrong. So you see how here, using the vanilla GAN, right, you get a collapse. And the collapse is that it's only really able to identify these 9 points here, right? So these 9, it's able to say, okay, this is real, and this is real, and this is real, and that's correct because there is real. That is what the real distribution is, but you see how it gets confused here. It doesn't quite have all of these points, all of the 25 Gaussians here. It only has basically 9 of them. It does have some parts here, right? But the Diffusion-GAN gets all of them. You see that? Gets all of the points, but it does have a bunch of other points which are maybe not as good. Like that seems a little sketch to me. Like the fact that the Diffusion-GAN, yeah, it gets all of them. It doesn't have this mode collapse issue, but it has a bunch of points here which are kind of nonsense. So I don't know, it seems a little sketch. And here they show you how this is vanilla GAN, and then this is with their Diffusion-GAN. And what are they showing you here? So they're showing you a number of epochs. So this is as you go deeper and deeper in training. So as you move in the x-axis, you're going further and further in training. The y-axis here is basically the confidence of the discriminator. So really, in order to train a diffusion or a GAN model optimally, you want the diffusion model to be like perfectly kind of on the boundary, right? So one way to think about it is you've heard about like in chess or in Go, right, where they say that if you want to learn as fast as possible a game like chess, you want to be playing against someone where you're going to win 50% of the time, right? If you're playing a game of Go and you're playing against someone who beats you every single time, you're not going to learn very much. And if you're playing a game of Go and you're playing against someone who always loses, you're not going to learn very much, right? And the same thing is true with a GAN where you have this generator and the discriminator. So if the discriminator is very, very good and says, okay, I can instantly know whether this is real or fake, the signal it's going to give to the generator is not going to be as useful as a signal from a discriminator that is a little bit more confused. And that's kind of what they're showing you here, is that with the vanilla GAN, the discriminator very easily gets basically much stronger than the generator. The discriminator is like, I know exactly whether this is real or fake. And that makes it hard for the generator to kind of learn and get better, right? Because it's basically getting beaten by the discriminator every time. Versus here, the discriminator and the generator, or the discriminator is much more confused, right? It's a little bit, it has to really try to pick apart the real ones and the fake ones. The classification model in the discriminator is not as confident, which means that the generator is going to have a easier time, or not easier time, but it's going to be better at getting kind of signal from the discriminator. So that's largely what they're showing you here, right? Right, and because the discriminator here is way more powerful than the generator, you get this mode collapse, where the generator has really only learned to basically about these 9 points in this two-dimensional space, as opposed to the real dataset distribution, which is 25 points. Versus here, when the discriminator is much more confused, the generator has a better, more informative gradients, is I guess the technical term there. And so you can see how it's better able to match the true dataset distribution, which is these 25 points here. So, I don't know, hopefully that was useful. But it's important to note that this this plot is for a toy example. So this might be happening in the toy example, and it might not happen in the image data set and image distribution. So like CFAR 10, like MNIST, toy examples, like they're great and you can understand them and it makes things easier to understand and intuit, but it's also not necessarily, you should take it with a grain of salt, because just because something works in a lower dimensional situation and with a simple situation doesn't mean it's necessarily going to be doing the same thing with more complicated distributions. To verify that our adaptive diffusion-based noise injection could benefit the learning of GANs on higher dimensional feature vectors, we directly apply it onto the discriminator feature space of projected GAN. Projected GAN generally leverages pre-trained neural networks to extract meaningful features for the adversarial learning of the discriminator and the generator. Okay, so you know how I was saying that here the generator and the discriminator are taking in images, so therefore they're probably going to have either a convnet or something that can basically take those images and turn them into a little latent vector, right? But here in projected GAN, what they're doing is they're going to be using pre-trained neural nets to extract meaningful features. So all that means is that they're going to take the images, and in this case they're going to feed them into efficient net v0, which is basically just a convnet. I'm pretty sure it's a convnet, efficient net v0. Efficient net v0 is, yes, it's a convnet. You see pooling. I'm pretty sure it's a convnet. I don't actually know. Let me make sure. Yeah, efficient net, rethinking for convolutional neural networks. So efficient net is just some convnet that's been trained on some classification task, probably ImageNet, and they're just freezing it, and they're using it to convert the images into aka little vectors, embeddings, or quote-unquote meaningful features, right? And then they're using the GAN to basically generate and discriminate in that feature space of the efficient net v0. Which verifies that our augmentation method is domain agnostic. I don't know, that's... domain agnostic is a very strong word, right? That domain agnostic, to me, it's like, do this with IMU data, do this with depth data, do this in text space, right? It's like there's so many different domains that saying something is domain agnostic is a very strong statement, and just showing that it works with efficient net v0 isn't necessarily, I think, a strong enough claim to claim domain agnosticness. Or maybe it's because this paper is old enough that, like, the fields of machine learning were separate enough that domain agnostic in this paper just refers to, like, image domain only. Maybe it's domain within the image domain, and I'm confusing domain and modality, but We see that with noise properly injected into a high-dimensional feature space, diffusion-projected GAN shows clear improvement in terms of both FID and recall. We reach state-of-the-art FID results with diffusion-projected GAN on STL-10. Okay, so they beat this paper here, projected GAN. But I mean, that makes sense because you're basically, projected GAN probably didn't have noise added to it. So really all you did is you showed that if you take projected GAN and you augment the input data, aka add noise to the efficient net V0 vectors, you're going to get a better score. But that's kind of like saying, hey, I trained something on ImageNet and then I trained something on ImageNet, but I add data augmentation and it performs better, right? It's like fundamentally the reason it performed better is because you're augmenting the data, right? And all this stuff that they're doing with the diffusion, like really, if you just like blur and look away, like it's at the end of the day, they're just adding noise to it, right? It's all just Gaussian noise. They're just like showing you that adding Gaussian noise is a kind of basic thing within diffusion. I feel like they should have done something more clever, right? I feel like they should have used a pre-trained diffusion model. That would have been like so much more interesting to me, right? It's like, imagine if the noise you were adding and removing from the diffusion model was coming out of a stable diffusion model, right? Then that would be so much more interesting because there would be like an additional, like the noise would be more interesting, you know? There'd be something to it. You could possibly learn something more. But the way that they're formulating this paper, they're not doing anything with the diffusion model. They're just basically adding noise that's Gaussian noise. So it's really just a really there's nothing diffusion-y out of this, right? It's basically they're just adding more or less Gaussian noise depending on the time step t, which is conditioned on the which is basically coming from the score of the discriminator, the confidence of the discriminator. But you didn't need to use a diffusion model there. You could have just defined an equation that does that without diffusion. Okay, so they do it with a bunch of other data sets. Blah, blah, blah. It improves whatever this instability is. FID results with different numbers of data. So, of course, if you use a very small data set, then adding data augmentation, you're going to get a much better score. If you already have a bigger data set, adding data augmentation, you're not going to get that much better of a score, right? So again, this is kind of just showing that fundamental relationship between the size of the data and the size of the model. So if you have a very small data set, you have to use data augmentation. You have to be as aggressive as possible with data augmentation, left, right flipping, adding noise, removing noise, cropping, all the different types of data augmentation if your data set is very small. But if you have a huge data set and it's like significantly bigger than your model, and then you might not even need to use the data augmentation, or at least it's not going to be as much of a difference, right? The difference between these two numbers here and these two numbers here. Conclusion, we present Diffusion-GAN, a novel GAN framework that uses variable length forward diffusion chain with a Gaussian mixture distribution to generate instant noise for GAN training. This approach enables model and domain agnostic differentiable augmentation that leverages the advantages of diffusion without requiring a costly reverse diffusion chain. Because you're literally not doing that. We provide theoretically and demonstrate empirically that Diffusion-GAN can prevent discriminator overfitting and provide non-leaking augmentation. We also demonstrate that Diffusion-GAN can produce high-resolution photorealistic images with high fidelity and diversity, outperforming its corresponding state-of-the-art GAN baselines on standard benchmark datasets according to both FID and recall. Okay. So that's that. I have a lot of opinions on this paper. I think that whenever they thought of this idea, what they were really trying to do is there's some papers that they start with a concept and then they extrapolate from the concept, right? But there's other papers where they start with two things, like, I don't know, like Gans and X, right? And then they try to mash it together. And this is very much one of those kind of mash it together kind of papers, right? And they promise this Gans with diffusion, right? Where you think that they're going to be doing something with diffusion models, right? With pre-trained diffusion models, you're going to have some kind of stable diffusion. It's going to be tricky in some kind of way. But that's not at all what they're doing. Really, the only thing that they're doing is they're just adding noise over a series of time steps, right? And it's important that they do that because here in one of their theorems, right, where is the theorem here? Yeah. The distribution of E is known and is independent of X. This is the problem. If they were to use stable diffusion, this would not be the case, right? Because I'm pretty sure that most modern diffusion models, the removal and the addition of noise is not just dependent on the time step, but it's also dependent on the information from the image, such as the class, or maybe some kind of something that comes from something that's kind of paired to the image, right? Such as the class label, right? That's the whole point of the guidance vector. So the fact that these two are independent is the problem. It's not a benefit. To me, it's an issue because it means that literally the noise is independent from the image. The noise is basically just Gaussian noise. So this is just an extremely fancy way of adding Gaussian noise to an image and augmenting a data set for a GAN task. So this is really just a really complicated way of doing a GAN where you're doing data augmentation. I think that's my primary kind of feedback, is that it's a little bit, it seems complicated for what it's doing, right? But I don't know, kind of cool, I guess. I guess it forced us to kind of do a bunch of math and learn a little bit more and get a little bit more comfortable, so maybe there's a benefit there. Either way, I appreciate whoever it was that recommended this paper. I already forgot your name, I'm sorry. But feel free to drop on the Discord and recommend more papers. You know, I'm always happy to read the type of stuff that you guys are interested in. As always, like and subscribe, join the Discord, join our community, and see you guys later. Hope you guys have a happy week. I think tomorrow I'm going to be looking at the GitHub, the new GitHub chat GitHub, or whatever they called it, Copilot chat. So tomorrow's going to be a little bit more programming heavy, not as much math and papers, but I think that appeals to some of you. Thank you. See you guys later.